Welcome, everybody. So we are going to continue talking about energy today. And in particular, what we're going to explore is representations that we can use for energy. We've already used a couple of these in the course so far, symbolic representations for energy and energy bar diagrams. But I want to introduce a new representation that can be really helpful. I'm going to do that by picking an example here, which is an example that we've thought about before. I'm going to throw this tennis ball up in the air. And that's all that's going to happen. I'm going to think about what happens to the ball as it moves upward and then back down to my hand. Now, we already know a lot about what is going on here because we know that the kinetic energy of the ball starts out really high at the bottom. And then as the ball moves up, it slows down and that kinetic energy is going to decrease until it gets to the top where it's not moving for a moment, no kinetic energy. And then the ball falls back down and gains kinetic energy. So the kinetic energy is changing as the ball moves. And the same sort of thing can be done for the potential energy of the Earth ball system, right? Down here, I have small amounts of potential energy. And then as the ball goes up, I get more and more potential energy, which is kind of offsetting the change in kinetic energy. We can represent that with symbols, right? It's easy for us to go right down. Things like, I know that the kinetic energy is equal to 1/2 mv squared. Oops. mv squared, right? Or that the gravitational potential energy is equal to mg times h, right? Those are perfectly reasonable things for us to write down symbolically. That's a good representation. We could, of course, draw a picture of like where the ball is, for instance, in time. We could also draw energy bar diagrams, right? We did that last week a little bit, right? Something where I'm saying, okay, I know I've got, some initial small kinetic energy, some initial small potential energy, and then over here I've traded this off, right? And I have less kinetic energy and more potential energy, something like that. So this would be K initial, U initial, K final, whoops, final, and U final, right? Something like that represents this trade-off in energy. But it can get tedious to draw a whole bunch of these, right? You can imagine that you might draw an energy bar diagram for every single point in time. That's a lot of diagrams, and I don't want to do that. So we can try to come up with a graphical representation instead. And the kind of graphical representation that we will come up with here is something called a potential energy diagram. And what it is a graph, kind of a traditional graph, where I graph the potential energy of my system, which we'll use capital U to represent, versus the position of the ball, right? So here I'm going to put Y or X or whatever variable you want to use for position, right? Where is the ball in its vertical motion here, right? I don't care if the ball is moving horizontally here. I'm trying to kind of throw the ball straight up in one direction. And so if I do this, I can think about how is the potential energy changing as I move from one position to another in the Y direction. And we already talked about this verbally. We can see what happens to it symbolically. This potential energy increases as I increase the vertical position. And in particular, right, you can see this H here, it increases linearly. In fact, H is actually a bad letter to use here. I'm going to go ahead and call this U as a function of Y, right? Where Y here is the vertical position of the ball. When I do that, it's really easy for me to draw this graph, right? I can go ahead and draw a graph that looks kind of like that. And if I were to say that this is maybe the total height that the ball travels, then the kind of peak value here is going to be this mgh that we're familiar with, right? And so you can see the difference here. H is a constant, right? How high does the ball go? Y is a variable, right? How is the ball's position changing as a function, right? So this is a potential energy diagram. One of the nice things about a potential energy diagram is it then will let us say other things about the other forms of energy. In particular, for this system, the total energy of the Earth ball system is constant, which means that if I wanted to, I could add a graph like so that is representing the total energy of the system. I could even think about what's going on with the kinetic energy here by subtracting these two graphs, because I know that the total energy is equal to the kinetic energy plus the potential energy. If I want to know the kinetic energy, I simply have to do E total minus U. Right? So that's something that I could graph on here if I wanted to.